And we are live as of 7 seconds ago. Everybody, apologies for the technical issues. We had to prepare a backup presentation here. Let me just fix this. Okay, so today we're going to hear from David Evans about CAN bus reverse engineering with Raspberry Pi using SocketCAN, a practical example. I think one of the great examples in this space, I mean, it's a thing that all of us run into immediately when you get into car hacking and automotive security. You start reading the Car Hacker's Handbook, and right there, first things first is SocketCAN. That's how you get started with some relatively low-cost tools. So before we dive into this presentation, just a little bit about us here. John isn't going to be able to join us today, but John's background is 15 years in automotive. He's leading security at Porsche. I'm Brandon Berry. I am the CEO at a company called Block Harbor Cybersecurity. I got into automotive cybersecurity in 2014. And as a company, we are working with automotive OEMs and suppliers to deal with this issue of automotive cybersecurity. So I got involved with the ASRG as the NAFTA region coordinator. I help lead all chapters in NAFTA. And yeah, so just a second, one more moment about the ASRG. We're seeing some really exciting growth. I think we're almost at 30 chapters and nearly 5,000 members. So really cool chapters popping up all over the place. I don't have that information handy, but really cool. Stay tuned with the ASRG because it is absolutely growing. There are people across the world that are joining the ASRG, that are starting their own local chapters so that they can learn more about automotive security or network with those local or gain access to this global network. The ASRG is working on a lot of exciting projects, including a member portal for you all. So that's underway. And yeah, so with all of that said, we're not going to spend too much time here talking about the ASRG. We're going to hand it over to David Evans. He can introduce himself, and we'll go ahead and get started here. Let me just switch over to your presentation, David. Here we go. All right.
Thank you very much, Brandon.
Good.
Hello all. Wonderful. So hello, as Brandon said, I'm David. So I'm just here today to talk to you about CAN bus reverse engineering with a Raspberry Pi. So start with me. So I'm David. I'm from Waterford in Ireland. I studied at Waterford Institute of Technology, also in Ireland, and I have moved to Cambridge in 2012. I work for Idiata Automotive Technology UK, and I work as a connected vehicle R&D engineer. I really enjoy just reverse engineering topics on automotive. So you'll see kind of me hanging around in Reddit car hacking. I really look forward to all the car hacking activities from Car Hacking Village, all the wonderful presentations that come out of there, and of course recently all the presentations that have been coming out of ASRG. I just also like to extend a thanks to John and the team at ASRG for inviting me here today. These presentations the past few weeks have been really interesting, quite nice. I also enjoy retro computer games reverse engineering. So there's a lot of ideas about let's call it speed running activities where the objective is to complete the game as quickly as possible, and a lot of technically minded people reverse engineer really old games to effectively complete the game more quick. I quite like this idea because these games going out in the likes of the early 90s and such, they had to be kind of, I guess, bug proof or able to work kind of without any updates. So there was no benefit of updating the software back then. And there's kind of a similar parallel to automotive in the sense that a lot of old vehicles had no over-the-air update mechanism back 15 or so years ago, and some of these vehicles could have some vulnerabilities that you may exploit through the CAN bus or other networks. I'd also just like to make it clear that what I'm presenting today is my own personal work and does not reflect the activities of my employer. I'm just going to talk a little bit about my 9 to 5. So Aplos IDIADA is a worldwide automotive engineering, testing and certification company, probably best known for our testing facilities in Spain. In my kind of role at IDIADA, I support a number of the R&D initiatives such as Secure IoT. So it's an interesting Horizon 2020 project, and we're doing some cool stuff on detecting attacks and kind of multi-industry applications, connected vehicle being one of them. The MUCA project, which kind of let two software-driven cars communicate over V2X and then collaboratively perform cooperative maneuvers together. And also Zenzik cyber feasibility study. So the UK government funded several projects recently on looking at the state of automotive cybersecurity. There is a lot of UK activity in automotive cybersecurity. We had Ian Tabor present a cool presentation recently on Car in a Box at ASRG, and also Ken Tyndall from Canis Automotive. He presented a really cool presentation on CAN bus security. If you haven't checked those out, I would encourage you to look back on that. And also I believe Vic Harkness is from F-Secure is presenting quite soon. F-Secure were also involved in that Zenzik project I mentioned there. I also represent IDIADA in kind of UK industry groups for automotive cybersecurity and connected vehicles. And kind of with that, there's a lot of interesting things happening in industry now with respect to automotive cybersecurity. So we've seen some cool presentations recently at ASRG on ISO 21434. And of course, the cybersecurity regulations for vehicle certification coming in soon will be very interesting. So what am I going to talk about? The presentation includes introducing the Raspberry Pi and SocketCAN tools. I'm going to present an example of segmenting data into a CAN data frame using SocketCAN, introduce some reverse engineering activities on a particular vehicle, an application I developed on the Raspberry Pi to support the reverse engineering, and a cool way I extended this application, a nice little demonstration, a very brief conclusion, and then we can take some Q&As. But first, before I get into this presentation, I do not advocate or encourage the injection of random data onto vehicles, especially when it's your own vehicle. There's a lot of things you may or may not know about the car, and if you just think you can inject random data onto the vehicle, I guess you have no idea what the consequences of that may be. And I would imagine your insurer might not be too happy about that if you've caused some harm to the vehicle, something broke, and you might find it difficult to explain to the mechanic trying to fix it. So throughout this kind of project, or throughout this exercise, I took a lot of very small iterative steps before attempting to inject messages onto the vehicle, because I kind of wanted to be quite careful and take my time, and especially try to understand what's happening and be quite confident what I'm doing and what the effect that will have. So what I kind of recommend is log and assess, log and assess, log and assess. Understand what's happening on the network, what are the implications of particular messages on the bus and what could happen. So, just try to be quite careful. Reason I really say this is because if you take away some information from this and I plan to share some small bits of code to maybe support your own activities. I just want to kind of say that if you break something or upset your vehicle in any way using information for this, essentially don't blame me, because, you know, I told you. So let's touch on the Raspberry Pi. So before I do, during my studies at Waterford Institute of Technology, Vector sponsored part of the course that I was doing. They provided lots of really nice tools, lots of nice software and training for our class. Absolutely great tools, but they're not very cost effective for, let's say, the hobbyist, you know, the kind of poor student, effectively. I was very fond of the Arduino Mega 2560. So again, going back to kind of the year 2010, this was kind of what you had to play with that, let's say, cost you under €50 or so. You can also buy Arduino CAN shields at the time, which were really, really useful. So it was just kind of about taking these ideas and these tools to kind of illustrate some or carry out some projects. So I used a combination of all of these on these projects. The project itself was quite fun. We kind of set up a half virtual network, half real network, and did some nice controls, turned on and off some LEDs, used a potentiometer to change a value on the CAN bus. A lot of fun stuff. I recently looked back on the code while preparing for this presentation, and it was very embarrassing. But also my wiring efforts, as you see, I've kind of cleverly hidden they're pixelated, because I was quite embarrassed looking back on something that I did about 10 years ago. So RaspberryPi Foundation started in Cambridge. It ultimately came from Cambridge. It's a really nice, small, powerful, and more specifically, affordable device. It got a lot of young people using Linux and just kind of getting much more familiar with those types of things. The kind of Raspberry Pi itself has come quite a long way since 2012. This is just an example here of someone running a Nintendo 64 emulator on the Raspberry Pi, which can be somewhat intensive or difficult to run. But you know, the kind of power capabilities coming out of these modules now are quite impressive. But also you can get some really nice CAN shields that kind of go along with it. So this is one of the kind of CAN shields I have. You'll notice on the kind of right hand side there's a little power module on it. So you're able to, so what I do is I hook into the OBD port and I draw the 12-volt power and ground from OBD, and use that to kind of power the Raspberry Pi in addition to doing the CAN activities. The SocketCAN essentially just enables the development of CAN applications under Linux. Really powerful tool, and it just really provides the ability to read and write CAN frames on kind of native interfaces, or what you might call real CAN, typically denoted as CAN 0 or CAN 1 if you're familiar with this, and virtual interfaces, which I think is really cool. It just gives you the ability to send and receive messages on somewhat of a virtual network, and that was quite important during my activities, which I'll get to a bit later. Essentially, the Raspberry Pi just makes it much easier to get up and running, and you can use some really nice tools available, such as CAN dump, which is just pretty much either print all the CAN messages out to a screen somewhere, or alternatively just log it to a file, create a log, and then use it later for some point. You might use CAN player, so you just recorded a log and you want to replay that log, or maybe you want to filter out some messages for kind of your analysis later on, because when you're collecting all these messages from the bus, there's going to be a lot of messages you're not really interested in. Just having the ability to apply some basic filters onto that and just help you out has been really helpful. CAN sniffer is really useful in the sense that you can just point it to some CAN traffic, and it will just give you the the kind of deltas, what has changed since the previous message, are quite useful if you're looking at some kind of messages which might be generated when you press a button, for example, which are not always being transmitted onto the CAN bus. So it's quite useful. And CAN send, sometimes you just want to double check all your nodes are active, or you can essentially transmit something onto the bus. So that's just kind of quite helpful to just, let's say, test something out. Maybe you have a termination problem on your bus if you have several of these Raspberry Pis all talking together, and just kind of running a CAN send, just make sure everything's up and running essentially. So there's a lot of kind of very useful tools and nice C++ APIs for your own development. So, I spoke earlier on about how we use some of the vector tools for this presentation, but as I kind of migrate to something that's a bit more hobbyist friendly, a Raspberry Pi, a power module, and an OBD cable, gives you a really nice starting point. So, how can we get up and running with SocketCAN? So we might just open up a terminal on our device, on a Raspberry Pi, and then just install CAN utils. So, pretty standard when you need to install something on a Raspberry Pi. You run a mod probe on vCAN. So this essentially just tries to set up a kind of virtual CAN interface for you to play with. As these are kind of like IP interfaces, or essentially an interface or a file description that you will use to transmit and receive messages, you just want to add this to your interfaces. So once you add this and then set it up, you can run like ifconfig. You should see your vCAN 0 there. And then, you have something set up. You might want to run CAN dump to just basically check what you have running. So this will just listen to virtual CAN 0 and just print out whatever it receives. On terminal 2, we just run the command CAN send vCAN 0 ID 100 followed by the payload. And you can see in those two images there, I'm using one terminal to send it, and the other is just receiving it. And that's pretty much it. You're kind of just using a few lines of code. You're pretty much up and running using virtual CAN. So now we're able to kind of send and receive data using a virtual CAN interface. Previously, we were just using an application to just do it for ourselves. To make our own application, you just set up a CAN socket to the interface. So this is when you might be running you want to develop your own application. You may want to send a particular message, every 10 milliseconds or every 500 milliseconds for whatever purpose you need to do. So you just need to kind of essentially create your socket in your C++ application. So you may have used like a TCP IP example before, and you kind of set up a socket. It's quite similar to that. So you're going to set up your socket, you want to specify the interface, bind to the socket, and now you can use the read and write functions to write directly to that interface itself. So what are we reading and writing on this particular socket? Essentially a CAN frame. This picture is used in nearly almost every presentation about CAN messages, which is really nice. It's a really useful diagram, but at the end of the day, this is what I'm kind of focusing on in this presentation. So the CAN ID, the CAN DLC, and the data. So these are the kind of things that, at least for my own activity, were the kind of pieces I kind of cared about. And yeah, so we kind of done earlier on just sending a CAN message on virtual CAN, and then it appeared in our CAN dump. But what effectively we would do in our own application to essentially do the exact same thing is we would kind of declare our structure for can frame. I just call it can fra. Then you just assign the ID, assign the DLC, and assign all the 8 values, and then just send it. That's pretty much it. Before I get a bit more into the reverse engineering, I want to just briefly touch on a can segment example. So this is kind of the concept, certainly the concept in this activity is where you take a value and you need to kind of segment it or spread the value across multiple bytes. So, you know, if we take an example like a float, which might be 4 bytes of value, you know, that's good. When we decide to stick that into our can message, then that's going to take up 4 of our 8 bytes, which is not quite useful. So if we just take a vehicle speed, going to be in a common value, we take, you know, we're working in meters per second. If we take the value 18.5 as an example, and we assume a minimum value of, you know, 0.00 meters per second, we will assume for this case that a 16-bit value is used. And just to kind of specify a maximum, we're going to say 122.87 meters per second, which works out pretty much at 440 kilometers an hour. So in our kind of message here, we might just say, right, define our MPS factor, which we're going to call it 0.01. So for every increment in our can byte value, it's going to just increment by 1, and that's going to be our unit, so 0.01. Our byte MPS is ultimately going to be our float value divided by our factor, and that just produces a nice kind of whole integer number for us to use. So you see there, I'm printing out the hex value of byte MPS, which is 073A, which is effectively 1850 in base 10. So, okay, we have a can message here. We're going to give it our ID 100. We're going to give it, again, we're just going to assume a message length of 8. We're going to clear our entire payload because at this moment in time, our frame data value is, you know, it's not set to anything. So just to make sure we're happy that everything in those values is effectively what we set it. We don't want some random values going in there from kind of, let's say, unset values or unset elements of an array. And then we're going to take our value. So I think it's the 07. So we're going to take the upper byte and then stick it into byte 1, and then stick it in the second part of that into byte 2. So this is just a really nice example where it just fits nicely into the message, and, you know, from a kind of human readable perspective, that's really easy. And the message gets sent. There's another ECU, some other module somewhere who cares about that message, and, you know, they whoever designed that module, you know, the kind of requirements for how that message is laid out has been agreed. But as we know, there's several CAN buses on vehicles. A lot of manufacturers may work hard to condense the amount of values on the CAN bus, and then they might go into much more effort to ensuring all the space is used up. So we're going to take this value that we used earlier on. Again, we're going to set our ID, set our DLC, clear our memory, and we're going to start off here by saying this C0 value, or more specifically C, the upper nibble of byte 1, so the upper 4 bits of byte 1, that's used for something else. It's something, nothing to do with us, nothing to do with this vehicle speed value. So that's fine, we just leave that alone. So we're going to take our byte MPS value, we're going to shift it down 12 bits. So really what we're interested in is the upper 4 bits of our byte MPS, which is hex 0. And then that goes in there, that's cool. I'm going to start on our byte 2, and we're just going to effectively put in 7.3 here, or hex 7.3 into byte 2. and then the lower nibble of byte 1, sorry, the lower nibble of our byte MPS, which is hex A, and that goes into the upper nibble of byte 3. And then, we have another value, B, used by something else, some other signal we don't care about. So, we assumed earlier a maximum of 1,122.87 meters per second, which gives us 12,287 when we use our factor. When we put in hex 2FFF, that's what we get in binary. And you'll see that in red, these, the two binary zeros in red will never ever be used because of how we specified that maximum value. So realistically, there is 14 bits being used there, 2 of which of our 16-bit value are not used. So, whoever designed this architecture can say, hey, there's 2 bits here which are going spare. Maybe you want to put 2 flags in there. Maybe it's the start of another value, and then the message gets sent. So there's many, let's say, clever ways of squeezing data into a small set of bytes. These are just some very high-level examples to kind of support the overall idea. But I've seen some very weird and wonderful ways of getting data into those bytes, and that's usually the case when you're trying to approach a reverse engineering activity. It can be quite difficult, but it's ultimately good to be aware of when trying to understand the system, because you're effectively looking at data. Hopefully it'll have some form of pattern that's easily recognizable, but you may need to consider, what's the endian? Is it assigned? Is it an unsigned? Is it 1 bit? Is it 8 bits, 16 bit, 32 bit? And that's what I'm coming back to earlier. It really helps to try understand what you're looking at. And just because, probably from a human readable perspective, we like things lined up, but I think with the case here that is not always the case, and quite a challenge to work around that idea. I'll make these examples available on Git soon for you to try and have a play with. I'll give you the transmitting application, the receiving application, and then you can have a play around and come up with your own weird and wonderful ways to segment data. So kind of moving on to the reverse engineering activity, I'm going to talk about the vehicle. So this is a 2010 model year vehicle. I believe it started its production in 2005, and then it was upgraded in 2009. There was a couple of things changed, but nothing major, essentially. It's a special variant of this particular vehicle. First of all, it has an Apple 30-pin adapter, so the old school iPod connectors and the early iPhone connectors. A USB cable, so I think this was just for some early MP3 players to plug in. Apparently this vehicle also supports MP3 CDs, but unfortunately I don't have any because it's 2020. And probably as well, you kind of the obligatory auxiliary cable. So if you have a device just for plugging in your your music player into it, and it just essentially takes over the radio. So kind of moving a bit more onto the OBD port. We have 2 CAN buses on this particular vehicle, diagnostics CAN and what I refer to as infotainment CAN. For the purposes of this, I'll be focusing on infotainment CAN. This particular CAN bus is running at 500 kilobaud, and up until now we didn't need to care about kilobaud, which is essentially the bit rate of the CAN bus. So this just running this command here, IP link set CAN 0 up type CAN bit rate 500,000. That just essentially configures your SocketCAN to work at 500,000 kilobaud. So, now we can start listening. So when I kind of go into the car, I just plug in the device and just start running CAN sniffer on the interface. I start to just play around with some of the buttons on the car just to, I guess, generate some activity. So, when you just plug onto the CAN bus, you're just listening. There's always going to be a set of messages that are just broadcasting. But sometimes you have some messages which I guess are generated when you press a button, or you unlock the door, you turn on the wipers, you invoke some sort of functionality, and then you may get a small period of time where new messages are on the bus, and then you may not hear them for another while. So I noticed some activity when I kind of changed like the radio station or the CD track, and a new set of messages appeared with an ID of 121. So I thought, okay, that's a bit interesting. Let's just have a look at that and see if there's anything interesting there. So I logged the CAN data. So that's what the -L does on CAN 0, and I applied a filter. So please only give me messages of ID 121, and the 7F0 is just a bit mask you apply on it. And this was pretty much what came out. And then it produced this on the screen. So I thought, okay, cool. So something happens on the bus when I change I press a button, the radio station changes, and then this is the data I get when that happens. Then I think to myself, that sequence looks very familiar. So now I have a log from the vehicle that I'm somewhat happy with. I can play this back using virtual CAN, and I'm kind of done with the vehicle for the time being. So go back into my home, load up my machine, my Raspberry Pi or my Linux virtual machine on my laptop, and then I'm kind of thinking to myself, I'm a bit suspicious of the first byte of that ID hex 121. So I'm kind of thinking to myself, is the following byte after that hex 30? Yes, it was. So that's quite interesting. And essentially, this is the exchange that's happening. So for every time hex 121 is sent, hex 521 is sent back. So on, so forth until the end of the data. And this is essentially isotp, or ISO 15765-2, which is effectively a way of transferring payloads of data. So let's just explain this a little bit more. So we have device 1, which is, we're going to call or refer to it as hex 121. It's saying I want to send a payload of length hex 3F, which is 63. So obviously you can't fit more than 8 bytes into your standard CAN messages. I won't get into CANFD, but the payload requires segmentation, and it needs to kind of, let's say that I want to send some messages. I'm going to send my initial starting frame, which is hex 10, to kind of establish a transfer. The remaining of bytes was the first 6 bytes of the payload. And then device 2 responds to say, yeah, I'm interested in that data. You're okay, keep sending, please. But only send me 1 frame each time, and then I will acknowledge you back. And also, please send it as quickly as possible. The rest of the message is just padding. And this is quite important because this is a flow control message. So hex 521 is saying to device hex 121, saying, yeah, you're okay to send me your payload, but I want you to send 1 message at a time. And hex 00 in byte 2 pretty much just says, there's no timing constraints, just send it as quickly as you can. If this was set to, I think the maximum time is 100 milliseconds. That I believe it's 100 milliseconds that to allow these messages to occur. So device 1 says, okay, here's one more frame. I want to wait for you to acknowledge it. And then this process pretty much just continues until we get to the very end, and hex, the entire payload is received. So just for reference, the payload ends at hex byte 1 of the second last row. So next to hex 29 of ID 121, there's a byte there, 00. The rest is just padding because this message always needs to be 8 bytes in length. So here's what appeared on the screen. Here's what the payload was. Is there anything here? As you can see in the image below, we have some text. So the FM station, the radio name, and the kind of preset number on the right. So you're able to scroll up and down through your predefined radio channels, and that's what that number 1 on the far right represents. We have some nice numbers. Is there a familiar sequence here? So kind of looking at this for a while, try to put 2 and 2 together, and then I start to see this happening. And then I'm thinking to myself, they look very familiar. Are they ASCII characters? Yes, they are. So there's, you'll notice that in the top left-hand corner, we have the characters F and M, which is represented as hex 46 and hex 4D. And then it jumps down onto the following line and then starts at hex 20, which is your ASCII space. And then it's pretty much just an entire string of 17 characters. So that's what I just tried to kind of show there. And that is pretty much it. So I'm assuming that device 1 is kind of the radio. Pretty much, it's quite likely. And device 2 just appears to be the LCD screen. So, let's gather some more logs of different occurrences of setting that text so I can use for comparison later to try to figure out what the rest of the data is. So I take this one here, which is RDSF-AF. You'll see a couple of differences between the previous one in the sense that we have 2 little arrows up and down, as well as some kind of underlying or little horizontal bars below, off and on. So having kind of poked around at this for a while, I see in red and orange, we have 3 bytes here, and it uses 17 bits to enable and disable the single line up and down. So across the top, above the text RDSAF, you have 17 single bars, and below you have 17 single bars. And then above you have these kind of thicker bars, and same for below. So they're all 17 bars in length. And so in this case here, we have orange is representing the bottom line. And we'll see here, this is representing the single line. So there's a single line below the characters O, F, F, O, and N. And that's what these bits represent. And it is represented in kind of orange bars there. And in purple and blue, we have 3 bytes here. So you see below in off, you have kind of a thicker bar. And the values hex 1C in blue is representing the thicker bars. We also have a little selector up and down arrow, which is represented in green in hex 0C. So that's, that's fine. So we figured out most of what's happening here. It's probably also worth mentioning, I mentioned earlier about isotp determining or dictating the rate of which these messages should be sent. So, when it comes to trying to do this, there's the LCD device, which is effectively sending the flow control messages, can be quite forgiving about timing, because ultimately, the Raspberry Pi is not a hard real-time system. It can be quite accurate, but at the end of the day, it's not, and it doesn't try to be. So we figured out what's happening here. Nothing that's too relevant or interesting. I had to then implement this exchange on the Raspberry Pi, so implement an application that would pretend to be the radio, and implement an application to emulate device 2 or the screen to, let's say, allow this exchange to happen, because running a CAN log doesn't really help you here. So if I was, because the flow control messages, are kind of running at possibly a different rate on the vehicle than they would be on like virtual CAN or my own application. I had to kind of develop the two applications together. So once I got to a point where I was very confident it was going to work on a vehicle, I was able to kind of populate text into those areas, and I was essentially confident that when I ran my application, provided some string of text, that it would behave essentially and do what I wanted. So just a very small reminder of what I needed to do. So I had to send my initial payload, so my first line, and then wait for the vehicle to acknowledge me, to say yes, send the rest of the payload, and actually have that exchange. Because this is what had to work in the vehicle for it to happen. So if we look at proof of concept, so proved it out in virtual CAN, was happy enough that it was working. Let's try it on a vehicle, and I hope the video comes across okay in this. Nice. And second, now let's try something a little bit more complicated. So just going back on that, it's worth remembering that for every time the screen updates, you still have to send those series of messages. So you'll see when you see the text scrolling across the screen, for each time the text scrolls, you have those messages sending out the entire time. So let's try something a little bit more complicated now. And here's just let's say the same data running back in virtual CAN. And yeah, so this task was a lot of fun, but what's the use case? I can put text on a screen, which is cool. It's a nice idea, but doesn't really serve any purpose other than impressing someone or just really showing what's happening underneath all the software. So let's try to do some control. The steering wheel has some buttons which are present on infotainment CAN. I assumed that once you pressed a button that it would, let's say, generate a new message, but after looking into it, the signal is always broadcasting, and when you press a button, I think it's broadcasting about just every 100 milliseconds. Really, it's not doing anything exceptionally clever. It's just setting a few bit values depending on the types of button you press. So we have in red here, simple volume control, up, down, and mute. And then in yellow, we have this steering wheel, just like a little rotary switch. So if you want to select your next radio station, your previous radio station, and also if you pull the button towards you, it kind of acts as like a select button, which is quite useful. So I thought, let's try do something with my phone. So earlier I mentioned an iPod cable, and then I had to source a little adapter that let me plug in the more modern iPhones. So how the iPod works in the car, it's pretty much just it's pretty useless. It only plays music. It bypasses the radio. Despite having a physical connection to the device, you can't change the songs. You can't increase the volume on the iPod, which is a bit unfortunate. But some would say that's an opportunity. So what do we have? We have an iPhone we can program. We have a Raspberry Pi that can listen to the steering wheel, populate text on the screen. Let's try something. So, if we can get the iPhone talking to the Raspberry Pi over IP, with the iPhone acting as the hotspot, another quite useful thing as well is just, if the Raspberry Pi has a connection to some little small hotspot like your phone, it just lets you SSH into it, and that can be quite useful, especially if you need to do some very quick changes. So I implemented a control mechanism between the two devices, so just a couple of messages that they could pass back and forth, and then the Raspberry Pi could say to the iPhone, please do something. The iPhone could respond with some information that the Raspberry Pi could receive, and then it could determine something. So the Raspberry Pi knows when when a button on the steering wheel is pressed. Can I iterate through a playlist and select a song from the iPhone? So I mentioned earlier that the iPhone, you have to open up the music app on the iPhone, select a song, press play, put your iPhone in the glove compartment, and then just leave it there. So, you can't change unless you make a really nice playlist. So I'm not sure if the sound will come across on this, but I hope it will be clear enough. So at the bottom of the screen, so we have, sorry, I'm just going to go back briefly. So what I'm going to talk about here is what is out of shot is I'm connected to the phone through the Raspberry Pi. I'm going to go through the list of songs that are available to me. It's a little bit faint, but you can see in the bottom of the LCD screen, you have the down arrow, which kind of represents you have more songs to go through. And the iPhone knows how many songs are in the playlist. The Raspberry Pi is just being told what to put on the screen. And then, this is just an app running on the iPhone that's, controlling things. So you will see below that I'm looking at some songs, just scrolling across the screen. So now I'm on the second song. So I'm just rotating the wheel on the steering wheel. Now I'm on my third song, and I think, okay, I want to play that song. You see here that the iPhone is not currently playing anything, but now I'm going to press the button again, and now my song is playing. That's cool. Okay. Then I'm I'm controlling the volume on the iPhone, so hopefully you've seen it there earlier, that the volume slider bar just went up a bit. And I think that's pretty much it. So now I'm gone back in, I want to look at another song. I'm going to say, okay, I want to play this song now. And it plays. And that was pretty much it. I'm not sure how that came across on your side, but hopefully it was at least understandable. So kind of coming back to a conclusion, a lot of work has gone into this, and there's still a lot more to do. Everything demonstrated was done with a Raspberry Pi and SocketCAN. The Raspberry Pis give you a lot of flexibility in kind of situations like this. So, being able to SSH into something, be able to quickly develop, prototype your own applications using a really well-supported device and something that's easily to come by, essentially. It's really useful. I hope you enjoy this. I'm quite open to collaboration, and should you wish, there's some contact details there to get in touch. So yeah, on the GitHub, I will make some of these, some of this code available for you to try yourself, especially the CAN segment one. It's also worth mentioning as well that there is an isotp implementation for as kind of a kernel module. So everything I was showing here, or at least all my applications, were working the the kind of user space as such. There is an isotp implementation for the kernel, which I would imagine is much better than what I made. But I kind of wanted to implement this myself more so as a learning exercise than anything else. And yeah, so I think that's it. Thank you very much, and I'll try answer any questions.
Okay, David, bear with me here while I fix my audio. Okay, it is all the way up. So hopefully the audience can hear me, but maybe they're more interested in hearing what you have to say anyway, David. So I didn't see any questions come through in the comments here. If you do have questions, paste them in the comments and I'll relay them to David, because I know David can hear me just fine. So David, you ran into, or you approached your car, you had a Raspberry Pi, you had a CAN interface, you utilized SocketCAN built into Linux kernel that comes native on Raspberry Pis. You learned and utilized isotp to build kind of a middleware piece of application. Did you get the chance to use any of the OBD at all? Any onboard diagnostics protocol information to mess around with data that's available on the car? Just because I know that's kind of a common starting place for people as well. You can get on CAN bus and start issuing some OBD requests.
Yeah, so what I forgot to mention was I will be providing that CAN segment example, and I used the example of vehicle speed. What I have done is I've created like a really small log of vehicle speed from the car, and I put that into a file. So one of the things I kind of struggled with is just ultimately, if I want to make a CAN message, half the battle is having some data to put into the CAN message, and especially some data that makes sense. So I kind of recorded a vehicle speed value, and I think it was every 10 milliseconds or every 100 milliseconds, and I was basically putting that into a file. So in the CAN segment application, which I'll make available, it uses that as your input. So if you want to come up with a clever way of segmenting the vehicle speed value, all you need to do is just implement that clever way of shifting around the bits and the bytes. Coming back to kind of the OBD question, I think especially in my line of work, you come across some times where you might just want to get some PIDs out of the vehicle. So like the standard kind of diagnostics request or kind of service requests for getting out like RPM or throttle position or vehicle speed. But I think for me, the more interesting thing is the kind of proprietary signals as such, the kind of signals that are kind of hidden away. They're not, really well known.
Right.
And that's for me, that's the more interesting thing to try work out.
Yeah, agreed. And I think that's exactly the logical next step. Once you're comfortable with CAN bus, with some of these transport protocols, isotp, once you're issued a few requests with onboard diagnostics, then you get really into the nitty gritty. The proprietary messages that go back and forth between ECUs on the CAN bus. That each automaker has a little bit different CAN messages, and so you gotta reverse each model of car that you're working on. Each make is different. And I think that's most of the challenge. Once you get kind of the basic, most accessible information, then you're stuck with a CAN bus full of data that you have no idea what it means. And without a DBC file or some kind of information from an OEM, it's hard to do much with it.
Yeah, and interestingly, when I was kind of, let's say, 95% through this presentation, I came across another project, and it was an older version of this particular car. And likewise, it didn't have the same implementation, but it had the same like message ID, and it just had a kind of, let's say, a different way of doing it. But what you'll kind of find sometimes is that message IDs, they may get reused from different vehicles, and I think with isotp, it allows you to use kind of the same underlying code, the kind of transfer protocol, but really the for the OEMs, they can implement that on their different model years, and the kind of unique part to that is how do you actually use the payload, and that can be quite interchangeable depending on which vehicle it is.
Yeah, that's right. So reused across OEMs and their makes and models, because obviously they don't want to redo work or re-encode things.
Yeah.
Or they want to be as efficient as possible. And by the way, just a shout out to OpenDBC. I don't know if you've made use of that, but there is a GitHub repo with DBC files from a lot of different makes and models to help you decode some of this information, at least be kind of accumulating reverse engineering efforts of people. So
yeah, definitely, and there's a number of companies who are very interested in people reverse engineering systems, and they kind of put out like bounties on particular vehicles. So I think they're more interested in some of the modern ADAS systems, but they do exist, and the people will pay for people to figure this out.
Yeah. So a few questions from the audience. Nico was asking about the infotainment button. I think you were showing the steering wheel. You had the ability to control the infotainment from there, but couldn't really figure out how that communication was done between it and the radio.
Okay.
So Nico was suggesting that maybe a BAP message, which, to be truthful, I'm not fully aware about BAP, but made a multiple CAN messages may be used there, and he's asking if you can play that message as well.
Yeah, and in fact I did. I just didn't include it in this presentation. So essentially, the little button module, let's call it, on the steering wheel is sending out a particular CAN message ID. Again, I think it was every 10 milliseconds or every 100 milliseconds. And essentially, the data in that CAN message was pretty much like mostly zeros, or just kind of mostly off. But when you press a particular button, it sets a particular flag, or maybe two flags, in that particular CAN message. So I didn't include it in the presentation, but
sure,
it's just really listening for that CAN message and checking if a particular bit is in set, and depending on what bit is set, you call a particular function on the Raspberry Pi.
Right. So that module broadcasting a simple message and just changing a bit if you're pressing the button.
Yeah.
Gotcha. So another question from Raul. So many modern cars have segmented CAN buses. You have dirty sides of CAN buses. You have clean sides where it's mostly a trusted environment. You have secure gateways in between them. I think 2021 vehicles have something like 16 CAN buses for some of the companies we work with. So, and most of those ideally aren't available at the diagnostic connector, because that's really easy access. So, have you encountered this in maybe this car or maybe another car where you had to gain access to more critical systems in the vehicle so that you could talk to some of the more important ECUs like your powertrain control module or your body control module?
Yeah. So obviously, this particular car I'm presenting, there's nothing, I guess, secure about it. There's two CAN buses that are exposed on the OBD port, and I just seen it more as an opportunity to do something fun. And the more modern cars, I guess if you're not afraid to kind of rip out parts of the car, you might not do it to your own car, but if you're working in this area, you may have access to cars, and you may be doing those types of things depending on what work you're doing. Then you can just kind of splice into the CAN wires, or maybe it's a different network. But I mean, it's kind of come back to you probably shouldn't do it on your own car, but
Right.
if you're working in the industry, then you may get the opportunity to.
Right, and we've been at bug bounties where automakers will give you access to their development vehicles, and what that looks like, Raul, if you're still listening, is you have to pull out a seat or you have to pull out some panels, and then you have to find the ECU you're after, or find the CAN bus you're after, and you're inserting a back probe into it, so you're gaining access, just not through the diagnostic connector. So it's a little more disassembly there, and you definitely, ideally, would have things like your wiring diagrams to show you around where some of these more important and critical CAN buses or other buses are on the car.
Yeah, no, definitely. And, I guess the more, some of the more modern systems now, you may have some version of Linux running, and, there may be some port left open, some like IP port left open, or some way into that system. And just kind of applying general reverse engineering tactics, then, you don't necessarily have to go through the CAN bus, but, and just being able to get into a system even wirelessly can let you have some fun as well.
So Clockwork has the next question. He is the critic of our audio. He is asking about tools in this space. So you talked about this a little bit. You use Vector in college. Vector, very expensive products. Their competitors are like Intrepid using Vehicle Spy. They're very expensive, but that's because their customers are typically automotive companies who are needing to do like signal analysis or simulation on their vehicles. So for us who want to hack cars, Clockwork's asking, would you really recommend a Raspberry Pi for this, or should you go for something more real time? I mean, there is a kind of a latency concern or bus speed concern at some point, especially if you're doing something like a man in the middle, where you're taking a message from one CAN bus and you're trying to not transmit it and instead send your own message.
Yeah. So one of the problems I encountered was when I increased the volume on the iPhone. So I used the vehicle's volume up button. That will always, because it's a broadcast system, the radio's always listening. If it receives that request, it will try turn up the radio's volume. Now, in the video I shown earlier, the iPod's music was playing, and that was overriding the radio. And I was just, let's say, catching that signal to do something else. And unfortunately, the radio just kind of updates the screen anyway. So I thought to myself, the radio is going to send that message, the initial message, to the LCD module. And I thought that in isotp, the kind of flow control message you send I was thinking that, I could try do a little man-in-the-middle attack by telling the radio module to essentially terminate the rest of that payload, which is pretty much just, the LCD module pretending to say, I'm not interested in that message, which is kind of like a part of isotp. But unfortunately, I couldn't detect the message quick enough to send the kind of generated flow control termination message with Raspberry Pi. So there was kind of a latency between detecting the message and then trying to tell the radio to kind of no, don't update the screen. And then you're getting into the Raspberry Pi was suitable for what I needed to do here. And I think in most cases for logging data and sending non-time critical messages, it works quite well. You could probably push it a little, get a little bit more performance, but I think at the end of the day, you may need something a bit more like a hard real-time system. And like the tools like Vector or Kvaser or Intrepid, it's essentially just find what you can that I guess suits your budget and your requirements.
Yeah, but it's definitely a good place to start. I mean, you can get a Raspberry Pi with dual CAN interfaces on it for under $200, and that gets you going. Two CAN interfaces allows you to do some interesting things. You could also go a different route and get USB interfaces that can plug into your laptop and just use a Linux virtual machine. All sorts of routes, but Raspberry Pi is definitely a fun one because you can leave it there. It's its own dedicated thing. You can leave it you can develop something and then leave the Raspberry Pi in your car. And not have to take it out every time.
Yeah, and I think the virtual CAN. So if you have like a laptop with a virtual machine, or just a machine natively running Linux, that's kind of, you can do probably 80% of your development in that virtual machine, and you get little time differences if you're on a virtual machine or if you're on real hardware, and like very minor differences, but. I think the kind of takeaway from this presentation is you don't necessarily need real equipment to, learn about this, to do some stuff at least.
So the next question from Patrick, who helps lead the ASRG, one of the chapters here. He asks, do you think it would be possible to reverse engineer a REST bus simulation for a specific ECU and get it to work with the hardware you used? And I think REST bus simulation here is talking about, well, if you have a simulated environment that is simulating, 50% of the ECUs because you don't have the whole car there. Will the Raspberry Pi be effective in that kind of environment?
Yeah, I think on a kind of R&D project I worked on, I effectively had my own module that I was working with, and I wasn't necessarily interested. This particular module was just listening to the CAN bus, and that's kind of all I had to do in that particular project. But the kind of come back to, I didn't necessarily want to work with a vehicle. So in the end, I had 3 Raspberry Pis with those 3 shields, kind of sending real CAN messages onto a bus, and I was just generating some traffic. And but more specifically, it was kind of traffic I was in control of, or traffic I understood. So I had like a simulation tool feeding the Raspberry Pi's data. The Raspberry Pi would just generate specific messages based on the data, and just kind of populated the bus to try reflect a real vehicle. And it only had about 30% bus load, which wasn't much, I guess, but it was kind of enough to let me do what I wanted. And just being able to do that with something under I guess, €300 if I had like 3 or 4 of these Raspberry Pis. That was kind of more than what I needed.
Yeah, and so to
And just
answer Patrick's question more succinctly, since I asked it in a roundabout way, you can use these Raspberry Pis to simulate release views, no problem. I mean, you can more or less do what you did here, which is replaying select parts of CAN logs over and over again in a loop on a Raspberry Pi.
Yeah.
Okay, so the next question from Clockwork. So do you imagine plugging in custom parts like a rangefinder? And so I think he's asking, we have Raspberry Pis here. I mean, one of the cool things about the Raspberry Pi is that you can plug all sorts of sensory inputs into it and do all kinds of things, not just with CAN bus, but let's just take a bad example. If you wanted to have a temperature sensor on the Raspberry Pi that if it detected a certain temperature in the car, it would start it to protect your dog in the backseat. I don't know, something like that. Do you kind of have any thoughts on that in terms of integrating other things and what you're doing with your projects here?
Yeah, I mean, there's plenty of things that you could do. One of these projects I started a long time ago, but unfortunately never finished, was trying to. I was able to. So this particular vehicle has a it's kind of manual transmission, but so I was able to work out whether or not I was in reverse, and I kind of came across some nice, really small, kind of night vision friendly or dark light friendly cameras, and I thought, you can get really nice small LCD screens for the Raspberry Pi. Could I tap into a particular signal, work out whether or not I'm in reverse, and if I am in reverse, turn on the screen, turn on the camera, and just kind of provide like kind of a retrofitted reversing camera. And I know there's many of those solutions you can kind of buy, but kind of half the fun is kind of making it yourself, I guess.
Yeah, I know for me, when I was in college, I'm interested in racing cars, and so rallycross is the area I'm interested in. And I was taking a look at how you could look at sensor data on CAN bus and other sensor data to try and detect a crash to warn other racers on the track that, hey, maybe there's a crash ahead. So it would kind of connect the racers on the track to help keep people safe. So the next question comes from Raj. He's asking about encryption on CAN bus. Is that a thing? So from my insight, I know it's a thing on future vehicles. I think some of the people in the comments are answering these questions as well. CAN bus encryption is kind of a thing, but bus speeds struggle to support encryption over CAN bus. So do you just want to talk a little bit about CAN bus encryption and automotive Ethernet and how that's kind of playing into this?
Yeah, I mean, I can try. So I think there was a really good presentation by Ken from Canis Automotive recently, and he touched on that topic a bit more, probably a lot more than possibly I could. Probably recommend checking that presentation out. There was one part I wanted to include in the CAN segment example earlier on. You can have some examples where we were just converting that application value, the vehicle speed value, and sticking it in a CAN message. You might have some values which never really change a lot, or change kind of very slowly. So for example, you might see a value go up when you are increasing your speed. You might see a value go kind of down as you're slowing down. that could be somewhat related to a throttle, that could be, but most likely it's kind of related to vehicle speed. I kind of had kind of a nice idea for introducing a CRC and a sequence counter. So, if you use a CRC, you take a value, which in this case might be your vehicle speed value, and you generate a CRC. So it's kind of a way to validate that message. But if you're calculating a CRC with the same value each time, you're going to get the same CRC. So, you could take a small example where you take a sequence counter and apply like a bitwise XR operation to it using the sequence counter. So you can put the CRC, the CRC, the sequence counter, and the application value in the CAN message, and then regardless if and you kind of applied the bitwise XR to the speed value. So even though the speed value is technically the same, so if let's just say you're kind of going along at 20 kilometers per hour, the actual value that gets sent in the CAN message is constantly changing. And I think that's more of the, security through obscurity more than anything else. But it's kind of a kind of mechanism like that would make it quite difficult, I think, to reverse engineer, because the value is constantly changing. You can't figure it out.
Yeah, and so I think someone later is saying that CAN's a broadcast-based system. How can you encrypt that? And I think there's a few things that we're concerned about in the security environment. We're concerned about non-repudiation, knowing that the message is coming from a valid source and not from your Raspberry Pi. I mean, this isn't what we're concerned about. This is what automakers are concerned about. Do we care if people can read the message? I'm not sure. Do we care if they can spoof the message? Definitely. So I think there's a lot of stuff in the works that is being enabled by faster CAN bus speeds with CAN-FD and automotive Ethernet and standard Ethernet making its way into the car, where you will start seeing maybe not encryption, maybe not full encryption, but definitely message authentication, and possibly even encryption, where there's a lot of different ways you can do that, but definitely at minimum message authentication to make it a lot harder to spoof messages on the CAN bus and just pretend you're an ECU.
Yeah.
So the next question, find it here. I guess that's the end of the questions. So really great questions, guys. Thank you everyone for putting these out. David, anything you want to leave the audience with before we close out here?
No, not particularly. This was something I kind of been working on a little bit in my spare time, and just thought it would be, a nice opportunity to present what I've done, and hopefully people found it interesting.
Yeah, and so, I really love that comment you had about collaboration. That's what the ASRG is all about. I hope that someone, reaches out to you and has some information to help you, and you can help them, because that is what this is all about, is finding ways to work together, make some fun things happen with information that is very sparse in this space. So David, really appreciate what you did here. I think it's a great example of how to enter the space and how to get started without some of these really expensive tools. How someone could kind of go out to their own car and look at this stuff, because that's a huge question in most people's mind is, do I want to be doing this stuff on my car when if I break it, I'll have to pay for it? Well, you can. You just have to be careful and safe and thoughtful about it. Understand what they're doing, not just going in and sending random messages on the bus or whatever. So really appreciate that. For those of you listening, join the ASRG Slack channel or Telegram channel. I don't have QR codes here handy. You can look at past presentations to get those, but get involved in the conversation. Take a look at some of our other webinars. I know we have a lot of exciting webinars coming up. A lot of new chapters coming online, like I was saying. And yeah, really appreciate you, David, and everyone else taking out their time. And we'll see you the next time, either in a webinar or in the ASRG chat. But I look forward to chatting further with you.
Thank you very much.
Okay, everyone. Thanks for the time, and yeah, have a good. What day is it? Thursday. Have a good Thursday. All right. Okay, we are offline.